Welcome back to the deep dive. You know, when you look at a modern competition row, whether it's a high-end recurve or a compound, it seems so beautifully simple, a really clean mechanism. And yet, attached to that handle is this seemingly chaotic array of rods and weights pointing in every direction. It just turns it into this complex, movable physics equation.
It is exactly that. It's a physics problem. And
Yeah.
for you, for anyone curious about optimizing that specific system, we've taken a stack of really technical sources on both stabilizers and just boiled them down.
Yeah.
So our mission today is to cut through all the jargon, right, to talk about mass, moment, and inertia, and give you clear, actionable principles for actually understanding and tuning your stabilizer setup.
Okay, so let's get straight to the core question then. Why do we even need all this complexity?
Well, the bow itself is inherently complicated. The forces are all asymmetric. The arrow leaves the string above your grip, the riser is cut away on one side, and then, worst of all, you get involved. Your hand position introduces this variable torque, and all this creates movements that, interfere with the arrow flying straight.
So that's what the stabilizers are trying to solve.
That is the problem they're designed to solve, yes. They control those unwanted movements. But, and this is a really crucial caveat, that all the source is stress. Stabilization is absolutely no substitute for good technique.
Right, it's a tool, not a crutch.
Exactly. If your bow behavior is consistently faulty, if you have major issues like rotational torque, you have to fix that fundamental technique first. Stabilizers are for refining. They don't fix major errors. Got it. Oh, so let's unpack this. Our plan today is to define the 3 essential movements we need to control, then explore the sort of counterintuitive physics of how weight and distance play these fundamentally different roles. And finally, look at materials and damping so you can tune the system for the smoothest shot possible. Let's start by defining the problem. What specific movements are these stabilizers actually targeting? Our sources seem to identify 3 specific domains of movement.
They do. The first is displacement. And this is just simple translation movement from one place to another.
Like a shift up and down or left and right.
Exactly. And before the shot, that lateral and vertical displacement is the most serious thing because it directly affects where you're aiming.
Okay, that makes sense. What's next?
Next is rotation. This is movement around an axis. We're concerned with 3, but the one we really focus on most is rotation around the vertical axis of the riser. It's what archers just call torque.
And torque is the big one. Torque is critical. It's so important because the bow is easiest to rotate along that long axis. So when you inadvertently torque the bow, the string actually moves sideways, and that launches the arrow laterally off the center line.
So stabilizers fighting rotation are what directly tighten your groups on the target.
They tighten that lateral spread, yes.
And the third domain.
That would be vibration. This is all that periodic movement, the buzz, the wobble, the rattling. It's just the residual energy left in the limbs and the string after the arrow's gone.
So what determines how critical each of these movements is? It sounds like it's about timing.
It's all about timing. We have to look at when these movements matter, and we can break it down into 3 periods. So before the shot, while you're aiming, any motion is it's completely undesirable. Here, lateral displacement and that sort of low-frequency vibration like your own muscular tremor, those are the enemies.
Okay, and then during the shot, that's a tiny window, right?
Yeah, a tiny, tiny window, about 15 milliseconds. There's very little time for movement here to affect the arrow's initial direction, but rotation, especially torque, that's key. During that high-stress moment, the bow is momentarily free to rotate, and that lateral movement directly impacts the arrow release.
Okay, and finally, after the shot.
Right. After the shot, the movement has no effect on the arrow that just left, but you're still there. Large movements, a lot of vibration, a poor feel that can cause an archer to flinch or anticipate the shot.
Or just get tired.
Or just get fatigued, exactly. This is where controlling vibration is crucial for consistency and really for the archer's longevity.
So if the archer often feels the vibration most, why do the sources seem to prioritize displacement and rotation first?
Because displacement and rotation directly affect the score on impact. Vibration affects comfort, wear and tear, and your consistency over time. But unless that vibration causes a big involuntary movement before the arrow leaves, it's not altering the trajectory of that specific arrow. You have to fix what makes the arrow miss before you fix how the shot feels.
That makes perfect sense. Fix the functional problems first, then the psychological ones. Okay, so now we move to controlling displacement, and that brings us straight into the physics of weight and movement. The sources make a really big deal about understanding the difference between this physics trio, Mass, weight, and inertia.
It's vital for choosing a system. Weight is just the force of gravity, acting downward. It affects how tiring the bow is to hold up.
Simple enough.
Mass is just the amount of material. But inertia, that's the key concept here. Inertia describes the difficulty of getting an object to move at all, whether that's up, down, or sideways.
So if I add mass with stabilizers, I'm directly increasing the bow's inertia, which makes it fundamentally harder to move in any direction. That's why a heavier bow feels like a more stable aiming platform.
Exactly. High mass equals high inertia, meaning it's harder to move quickly. And that resistance to quick movement is precisely what we want during aiming and during the shot. But, and here's the fascinating wrinkle, things change when the shot happens really, really quickly. We need to talk about static versus dynamic properties.
The speed difference. What happens in those few milliseconds when the bow goes from still to being hit with these huge forces?
The shot is so fast that objects take time to start moving. So if you use long, flexible stabilizers or certain kinds of rubber joints, the bow can briefly behave as if it's unstabilized during those milliseconds of the shot. It just takes time for the weight at the end of that flexible rod to fully react and exert its inertial resistance against the bow's sharp initial kick.
And this leads us right to this famously misnamed accessory, the TFC, or Torque Flight Compensator.
Yes, the TFC is a bit of a historical misnomer. Originally, it was introduced as a flexible joint. The idea was to maintain a smooth, static feel-so, the balance before and after the shot, while allowing the bow to behave normally during that very short high-force shot window where the weight at the end hadn't really caught up yet. It didn't compensate for torque. It allowed the bow to retain its static balance without messing with the dynamic rotation.
So the original TFC wasn't even about damping, it was about flexibility and feel.
Precisely. Now, of course, the concept has evolved. Modern adjustable TFCs are valued primarily for their ability to absorb and tune vibration, because the materials they use, often rubber or viscous joints, are excellent at damping. We'll cover that in detail later, but historically, yeah, the name just referred to its flexible joint.
Okay, this third segment gets to the heart of the aha moments in stabilization, controlling rotation and balance. This is where distance apparently matters more than weight. So let's tackle balance first, controlling the bow's roll.
Static balance determines how the bow rolls after the shot. This is all about the center of gravity, the CG, relative to the suspension point, which is your hand grip. If the CG is in front of the grip, the bow rolls forward. If it's behind, it rolls backward.
And a controlled forward roll is what everyone's aiming for a good feel. The sources suggest a bow behaves pretty well with the CG, within about 20 centimeters forward of and below the grip. And this is where we get to that first critical concept, moment.
The physical principle governing static balance is simple. Moment equals mass times distance. And this gives us our first crucial rule of thumb for balance. Half the weight at twice the distance has the same effect on balance.
That is the core principle of a long rod setup right there. So if I have, say, 6 ounces on a 15-inch rod, I could swap to a 30-inch rod, put only 3 ounces on it, and the balance, that forward roll, would feel exactly the same. You can totally change your geometry without changing your overall roll.
Right. But if distance is so powerful for balance, why aren't we seeing rods sticking out 5 feet from a bow?
Besides the obvious practical limits.
Exactly. We also have to consider the dynamic balance kick.
The movement during the shot itself.
Correct. During the shot, your bow hand is exerting this massive forward force 5 to 10 times the effect of gravity. So if the overall center of gravity is too high, say you have really heavy weights placed high up on V-bars or a top stabilizer, the bow will tend to kick upward initially, even if gravity later makes it roll forward nicely. So weight placement is just as critical as overall weight.
Okay, so moving from that static balance to dynamic rotation controlling the torque, the math gets even more powerful. This is governed by moment of inertia, which is what resists the rotation itself.
Right, and moment of inertia is defined as a mass multiplied by the square of the distance. And because you are squaring the distance, the effective length is just hugely magnified. This leads to our second and most powerful rule of thumb for rotation control. A quarter of the weight at twice the distance has the same effect on rotation.
A quarter of the weight at twice the distance. That is the clearest evidence that to cut rotation with the minimum amount of weight, you have to use small weights on very long rods. That long rod sticking straight out is doing enormous work against torque just because its distance from the axis gets squared in the math.
Exactly. The long rod has a large effect on reducing rotation around the riser. And while twin short rods and V-bars also have moderate to large effects, the sheer length of that long rod makes it the primary anti-rotation device. This is why you have to prioritize lengths when you're battling torque and only add weight when you need it for inertia or for balance.
So if the last segment was all about the geometry of mass and distance, this one is about materials and energy dissipation, controlling vibration through damping. This is really key to the overall feel and consistency of the shot.
Right, vibration is periodic movement, so it has frequency, measured in hertz, and amplitude. And to tune a stabilizer system, you need to be able to shift or absorb that frequency. We've got two simple rules. A stiffer or shorter rod gives you a higher frequency, and conversely, a heavier weight gives you a lower frequency.
So how does the stabilizer actually kill that energy? This is where choosing different materials comes in, right? Turning that movement into unusable heat. If we're trying to choose a stabilizer, what are the different methods we're actually paying for?
There are four key ways materials dampen energy. The first is friction. This is used in stabilizers that are powder-filled or foam-filled. The movement of the material inside the walls just dissipates energy.
Okay, second.
Second is fluid or viscous damping. Think of a shock absorber on a car. This is used in hydraulic systems where a piston moves through oil. It's excellent for smooth, powerful energy transfer.
And third is hysteresis effects.
Right. This is energy that's lost when rubber or viscoelastic materials like doinkers, limb savers, or the rubber joint in an adjustable TFC when they stretch and return. They don't give all the energy back as movement. Some of it is lost as heat. These are often used as simple, cheap add-ons to fight localized buzz.
And finally, structural effects. This is where the choice between, say, carbon and aluminum really matters.
It matters a lot. Carbon rods, because they're composites, absorb high-frequency, post-shot vibration much more effectively than aluminum rods, which tend to ring and transmit that energy.
So that material choice is pretty crucial for the application.
Absolutely. If you need maximum stiffness and lighter weight, modern high-modulus carbon is your choice. It gives you superior structural damping against that high-frequency buzz. But if you need to add a lot of mass and you don't mind the weight, or maybe you plan to fill the stabilizer with powder for friction damping, then alloy rods are an option. But they usually require more secondary damping accessories to feel good.
And all this damping is necessary because we have to actively prevent the danger of resonance.
Resonance is the amplifying force. It's what happens when two systems, like your own muscular tremor, which is a low frequency, or the bow limb's natural frequency, a high frequency vibrate in concert. And this leads to greatly amplified, sometimes uncontrollable movement during aiming or after the shot.
And the fix is usually pretty simple. Avoid it. Change any part of the system, weight, length, stiffness, to shift the natural frequency away from the problem one.
And this is where the modern tunable damping of the adjustable TFC comes back into its own. The tension on these units lets you make continuous adjustments. You can literally tune the system to match and dissipate a specific vibration frequency.
Okay, so give me an example. If I have a low-frequency aiming wobble, how do I tune the TFC for that?
For a low-frequency aiming wobble, which is often your muscular tremor or a slow bow movement, you need low or soft tension and a medium to long rod length. This gives you a soft, slow-motion damping effect. But for high-frequency post-shot vibration, you need tight tension and often a shorter rod length. The system needs to be stiff enough to capture and dissipate that energy instantly.
Okay, we've covered the movements, the physics, the materials, the accessories. So what does this all mean for you when you're assessing your own equipment? How should you approach choosing a system?
The sources all recommend a sequential decision process focusing on those three domains we talked about, and in this specific order.
First, decide on weight. This is about your overall inertia and stability. It's your initial choice. How much mass can you comfortably hold? A simple carbon rod is light, but if you need higher inertia or better low-frequency damping, you might choose a filled or hydraulic system, which will be inherently heavier.
Second, decide on balance. This affects your forward and backward center of gravity and that post-shot roll.
Yeah.
Use the moment principle. Figure out if you need to achieve that balance with short, heavy side rods or long, light ones. And remember that weight placed low often helps minimize that dynamic upward kick.
And third, you select your damping. This is where you finalize the accessories and materials. You choose carbon fiber for high-frequency absorption, and then apply specific viscous or hysteresis accessories like doinkers or TFCs to target any specific frequencies that are left over, whether that's aiming wobble or post-shot buzz.
And once you've built a system based on those principles, you have to assess it. Of course, objective tests like your score and your group size are essential, but systematic subjective assessment is just as valid and necessary.
The feel factor.
Exactly. You have to ask yourself, how does the bow feel? Is the shot smoother? Does it recover cleanly? The overall feel is a necessary part of the process, because if the setup promotes confidence and it prevents you from anticipating the shot, it promotes consistency. And that ultimately improves your objective score.
This has been a true deep dive into mechanical control. We've defined the problems. Mass fights displacement, moment controls balance and roll, and damping controls vibration.
And the selection of materials, from the high-frequency absorption of carbon to the powerful tunable control of hydraulic or viscous systems, that directly determines how you solve those problems. It's truly this interconnected web of geometry and physics that turns a bow into a stable platform.
And here's where it gets really interesting for your next tuning session. Since changing distance has a squared effect on rotation, meaning twice the distance requires only a quarter of the weight for the same rotational control, but only a linear effect on static balance. Imagine how radically you could redesign your bow's setup. Could you significantly reduce your overall stabilizer weight while maintaining the exact same rotational stability just by maximizing the length of your long rod? Now go measure your system and see what happens when you start squaring the distance.